This is the Tree of Life, Season 15, Chapter 2. In this episode, we will be talking about how structural changes in conformational entropy as between two or more structures decrease or stay the same, consistent with the second law of infodynamics. In the last episode, we analyzed changes in conformational entropy from one structure to another in light of assuming an increase, or at least equal level of conformational entropy, as between two structures. What we observed was that it appears to be consistent with the binary logarithmic relationship between the periods associated with distinct structure members for the conformational entropy to remain the same between an old and a new structure. What we also saw was that for the conformational entropy to increase from an old structure to a new structure with more structure members would require a departure from the binary logarithmic relationship between the periods corresponding to phase shifts for those structure members. Thus, from this, we can see that it is more consistent with what we have observed to say that conformational entropy must decrease or stay the same from an old structure to a new structure. This is a rephrasing of the second law of infodynamics. From this we can draw some conclusions. If we observe that during some time frame p, the number of structures to which a person B is involved is equal to x, then the total change in conformational entropy from structure 0 through x must stay the same or must decrease. Thus, if there are say two interactions with two structures during time p, then the conformational entropy of structure 1 must equal or be greater than structure 2. This means that the small shifts in conformational entropy associated with those two interactions must either equalize structures 1, 2, or result in a reduction from 1 to 2. This means, for example, if structure 1 is a new structure created by interaction 1 involving 9 structure members, and structure 2 is an existing structure creating interaction 2 involving 5 structure members, then the change in conformational entropy through these two structures must equal or decrease. Thus, we imagine that, let's say for structure 1, comprised of persons B, C, D, E, F, G, H, I, the conformational entropy occurring over 256 seconds means that the period for person B is 256 seconds. The period for person C is 128 seconds. The period for person D is 64 seconds. The period for person E is 32 seconds. The period for person F is 16 seconds. The period for person G is 8 seconds. The period for person H is 4 seconds. The period for person I is 2 seconds. This means that the 256 total conformations is reduced to 128, because person B does not flip phase during the measuring period. We know that the entropy of this structure is equal to the negative sum for all the states of the probability of a state times the logarithm of the probability of that state, and we know that the entropy of structure 2 must be less than or equal to structure 1. Thus, structure 2, because it is only a 5-person structure, will have 16 conformations so long as the period of the longest phase flip is greater than 16 seconds. If we calculate that the Shannon entropy of the first structure is 2.107, then the highest entropy associated with the second structure, being 1.204, is less than the entropy of the first structure. But what if we assume that for the first structure, the entropy is lower than 1.204? i.e., if persons B, C, D, and E don't flip phase in the measuring period, i.e., the measuring period is less than 64 seconds. Then we can say that the total conformations is only 16, as the 9-person structure becomes conformationally equivalent to the 5-person structure. In this case, the conformational entropy would be the same in both structures. Now, if we imagine that for structure 1 the measuring period is less than 32 seconds, and persons B, C, D, E, F don't flip phase, then we can see that in order for structure 2 to demonstrate less conformational entropy, one of persons B, C, D, E must also not flip phase during the measuring period. This means that the measuring period for interaction 2 in relation to structure 2 must be less than 16 seconds. Thus, we see that conformational entropy requires a corresponding shift in the interaction period when there are different numbers of structure members, as between sequential interactions. Thus, we also see that the operations described as structural adjustments reflect conformational entropy shifts between structures corresponding to distinct interactions. I.e., a nonlinear displacement event flips the phase with respect to an otherwise static system member, representing an adjustment in conformational entropy, as between two interacting structures caused by an interaction. I.e., if we see the elongation of phase corresponding to a structure member, it results in lower conformational entropy to a structure during the measuring period. Thus, to prevent this slide in conformational entropy available for future interactions, a phase shift is compelled with respect to a static arrangement. Thus, we must imagine that sequential interactions between structures act like rails directing the gradual movement of conformational entropy downward or sideways. That's the end of the podcast for today.